Hello, and welcome to MiniLecture 14 on the product and the quotient rule. Alright, so in the last couple of lectures, we've introduced some derivative rules, including the product and the quotient rule and how to sketch the derivatives. And then in the last lecture, we talked about how to use the power rule, where you have the derivative, for example, d by dx of x squared, or d by dx of 1 over x squared, or the derivative of a root. In this lecture, we're going to talk about how to take the derivative of a product of two functions, or the ratio of two functions. Alright, so let's start with the product. If we have the derivative of two functions, f of x and g of x, this is equal to the first function, f of x, times the derivative of the second function, plus the second function times the derivative of the first. Now, it sometimes helps to write this in simple prime notation. So if we have u times v prime, this is u times v prime plus v times u prime. All right, let's see how this plays out in practice. Suppose we have the function h of t is equal to the square root of t times the polynomial a plus bt. All right, now we can see that this is actually the product of two different functions. This is our u, and this is our phi. All right, so we have that u of t is equal to the square root of t, and v of t is equal to a plus bt. Now we need to find u prime and v prime so that we can plug them in there. So first of all, let's take d by dt of t. Now, remember that a root is the same thing as a fractional exponent. So this is the same thing as saying d by dt of t to the 1/2. All right, now we can use that power rule that we had before. And this simply becomes 1/2 1 over t to the 1/2, which is equal to 1 over 2 the square root of t. All right, so that is a bit complicated. Now let's do the next one, d by dt of a plus bt. Now, we can split it up on the sum. Note that this a is a constant. Even though it's unknown, it's still a constant, so this is simply going to drop out. So this goes to 0. The b, similarly, is a constant, so it is going to factor out, and so we have that this is b dt dt. Now, you could either apply the power rule to take this derivative, or you could just note that the numerator here is the same as the denominator, and we can think of this as going to 1. So this is simply going to be b. All right, now we're going to calculate this product. So we have d by dt of h of t is equal to u, which is the square root of t, times the derivative of v, which is just b, plus v, which is a plus bt, times the derivative of u, which is 2 the square root of t. All right, so rewriting this for simplicity, all over the square root. All right, so now you have taken the derivative of a fairly complex function here. All right, why does the product rule work? Well, let's think about what the derivative is. The derivative says, how does this function change as I change my independent variable by a little bit? So let's think about the function f is equal to u times v. Another way of thinking about u times v is as the area of a rectangle that it has u length here and v length there. So this function f is the area, represents the area of this blue rectangle. When I take the derivative, I'm asking, how does this area, how does this function f change as I change my independent variable du and dv just a little bit? So if I change these two axes just a little bit, how does the area of the square change? Now, we can see that how this area changes by adding up all the different rectangles. So first of all, I have the change u times dv, and I have the change v times du, and then I have this change du times dv, delta u times delta v. All right. Now note that the derivative is how this area changes with a very, very, very tiny change in u and a very, very, very tiny change in v. So we want to ask, how does the area change as this distance here gets really, really tiny and this distance here gets really, really tiny? So let's draw another example of this area where that delta u and that delta v are a lot smaller. All right. So if I do that, you can see that the area of this rectangle didn't change a whole lot. The area of this rectangle didn't change a whole lot, but the area of this gray component of it shrunk enormously. So as we take the limit, as those deltas go to 0, which is the definition of a derivative, this gray rectangle drops out, and all we're left with is these green rectangle and the red rectangle. So what I end up with is that the derivative d by dt of my function f is equal to the green rectangle u times dv dt plus the red rectangle v times du dt. So just to make this clear, let's turn this into the red rectangle, and this is the green rectangle. All right, and that gives me the derivative of my area of my function. All right, so that's the why behind how the product rule works. All right, what about the quotient rule? Well, the quotient rule doesn't have very nice, corresponding nice version of this geometry, but you will see in a couple of lectures that you can actually derive the quotient rule using the product rule, but you need the chain rule in order to do that, so you can combine derivative rules to get the quotient rule from the product rule. So let's just talk about what the quotient rule is without explaining why, and we have the function f of x divided by g of x. This, once again, is g of x d by dx of f of x minus f of x d by dx of g of x times the derivative in the denominator. So it's low d high minus high d low all over the square of what's below. This is how you would write it in prime notation. So let's see how this plays out. Well, in contrast to the product rule, where it sometimes can be hard to define what u and v is, it's more easy in this case because it's just simply the numerator and the denominator. So what do we have? The numerator is 3x minus 1, and the denominator is x squared. Now let's differentiate those two things. U prime, all right, so now we want to factor out this 3. Then we want to take x, the derivative of x. This is the power rule. That 1 is going to go down, and we're going to subtract 1. This simply becomes 1. Now, we could have split this derivative up on that difference, so we'd have minus d by dt of 1. Now, you guys know what that is. It's simply 0 because you're taking the derivative of a constant, so this is simply 3. All right, what about the derivative of v? Once again, let's apply the power rule. So we have 2x to the 1, which is simply 2x. All right, now let's put all these pieces together to get the quotient rule. So we have low d high minus high d low. Oops, I totally messed this up. Sorry. Let me start over. So we have low x squared times d high, which is 3, not 3x minus 1. All right, minus high 3x minus 1 times the derivative of the bottom all over the square of what's below. So we have x squared squared. All right, so this, once again, this here is v times u prime minus u times v prime all over v squared. All right, you can simplify this a lot, and I'll let you do that algebra on your own, but if you simplify this, you're going to simply get that the derivative d by dx of L of x here is equal to 2 minus 3x all over x squared. Or no, sorry, x cubed. All right, so that is the quotient rule. All right, now let's introduce these two special derivatives. First of all, we have the derivative of the function where the function remains unchanged, and that is e. So this is another reason e is special. So if we take d by dx of the function e to the x, we simply get out e to the x again. Now, if we have d by dx of ln of x, this is 1 over x. And you're just going to have to remember these two derivatives. So I don't ask you to remember a lot of things in this class. These are the two things that you're going to have to remember, that if you take the derivative of e to the x, you simply get e to the x. And if you take the derivative of the natural log of x, you get 1 over x. All right, so let's see how we can play these out in practice. What about d by dt of e to the t plus 17? All right, note that first of all, we can split this derivative up on the sum. The derivative of a constant is 0, and this simply becomes e to the t. All right, what about d by dx of ln of x times 1/3? That 1/3 gets factored out, and we have d by dx of ln of x, and this is simply 1/3 times 1 over x. All right, now finally we have the derivative of some log that does not have the natural base. So recall that the log here, when we don't write the base, actually has a base of 10. So how do we take the derivative of log base 10? We only have the rule for the derivative of log base e, but we're wanting to take the derivative of log base 10. How do I do this? Well, we have to use our logarithm rules. And so we can change the base of a logarithm by simply writing this as d by dx. Now let's change that base. So we're going to have the natural log of x divided by the natural log of 10. So just to remind ourselves, we have a little 10 here, and we want this to go there and this to go here, and here is our new natural log base. All right, we got there. Okay, now what do we have? Now this part, we know how to take the derivative of that. Don't be misled by this natural log of 10. This is the natural log of some number 10. That is simply a constant. So if you could plug this into your calculator, you would get out some number. So this is simply a constant. So it just comes out. So we have 1 over the natural log of 10 times d by dx of ln of x. All right, now we can simplify this even further, and we have ln of 10 times 1 over x. So this one rule actually lets you take the derivative of any logarithm base by doing a change of bases first. All right, so with that, I'm going to leave you with a self-study question where you're going to practice those principles, and I'll see you in class.